All right. So, happy Monday. Welcome to class 3. We are going to be talking about the role of performance in a computer design, right? So, whenever we talk about buying a computer, we'll look at its performance. But what about its performance do we look at? Like, how do we quantify performance? So we're going to do this in 2 lectures. We are looking at part 1 right now. In class 4, we will be looking at part 2. There's a question in the chat box about homework 1. Like I said, I will be posting homework 1 later today. It will not be due until Thursday of next week. Another question is, will the material we cover today be the last lecture that is on the homework? No, actually, it'll be the first thing that is on the homework. So things that we learned today and on Thursday will probably be the most important things for the homework that is due a week after Thursday. So you have some time to work on it, but it'll be mostly related to performance. Okay. Now, whenever you think about buying a computer, you say, I need performance, right? But it turns out performance cannot be one thing, just one thing that you look at. You have to look at it in from different angles. So for computer engineers, that's our business, right? Improving the performance, and only the best survive. So in terms of computer designers, people at Apple and people at working with Intel chips at Microsoft, these are kind of the businesses that have survived for a long duration of time, right? And they were able to do that because whatever the users, the customers were looking for, they were able to provide those aspects of improvement. Now, when you look at just the performance, you would say, all right, I need a faster CPU, right? CPU speed, that should be the fastest. My processor should be the fastest. Or you might say your overall computer speed. Now, what is the difference between CPU speed and overall computer speed? Well, CPU speed just looks at the processor speed, right? Just the CPU. But when you think about the computer speed, then a lot of other factors need to be addressed. For example, the operating system comes into the picture. The I/O devices come into the picture. The bandwidth that is present between the CPU and the memory, right? How fast the communication can happen between memory of a computer and the CPU. That also comes into the picture. So many other aspects need to be looked at when you look at overall computer speed. And performance can also be looked at from the angle of cost and power, right? Are the computers cheap or not? Is my computer getting heated up, or is it staying cool to even deal with complex computations? So you look at cost and power. You also look at what am I paying to get a specific speed. Now, when you go down to the lower levels of quantifying performance, you look at these two more important things. Those are throughput and response time. Throughput is what? Throughput is throughput or bandwidth number of tasks completed in a given time. Right? How many tasks is my computer able to finish in a given amount of time? That's throughput. So sometimes a computer might, or a user might be interested in increasing throughput as much as possible. Response time is another metric in which you could quantify performance. What is response time? Also called as execution time. Well, this is the time it takes from start of a task to finishing a particular task. So this is just one task, right? So start and completion of a specific task. Specific task. So a lot of times you may want to reduce response time, right? I want the response to be as fast as possible. Let's talk about performance with this example here. Example 1. I have a computer with a 5 megahertz CPU. So can I say that a computer with a 5 megahertz CPU runs 25% faster than another computer that has a CPU with a clock rate of 400 megahertz? With everything else being the same, can I say that or not? Now, the short answer is no, and here is the reason why. Even though this computer is 500 megahertz and this guy is 400 megahertz, the clock rate alone does not determine whether the computer is overall faster or slower, because there are other things involved. For example, if you strictly look at execution time or response time, you have two major components in this. There are other components apart from CPU time and IO time, but the major time sinks are CPU time, which is what? Which is the time a particular task spends in the CPU, right? That's your CPU time. Then you also have IO time. How much time is being taken because of data moving from an IO device to the CPU, to the memory through the CPU, right? So that's IO time. So even if this is unchanged, because of improvement in the performance, we may decrease the CPU time or we may not decrease the CPU time, right? So that depends. Let me take a look at this in a slightly different manner. So I'll add a page here. So we had two cases here. One was 500 megahertz and the other was 400 megahertz, right? And what are these? These are the clock rates. And the reciprocals of these clock rates will give us clock cycle time, right? So clock cycle is 1 over clock rate. So if we found the clock cycle time for each of these cases and start sketching up a square signal, that's your clock, and it's periodic and it's repeating at a particular frequency, right? 500 meg or 400 meg, depending on which clock rate you're looking at. So if you have, say, one instruction, right? So suppose you have an add instruction and your processors are trying to complete this add instruction. And say, for the sake of discussion, that the add instruction takes 2 minutes. In that case, does it matter which processor I use? Does it improve performance if I use 500 meg or 400 meg? If the add instruction is taking 2 minutes, does it matter which processor I'm going to be using? No, absolutely right. Because it takes 2 minutes, no matter which processor I'm going to use, I'm going to be taking 2 minutes for this. However, if it was 2 cycles, then it starts mattering, right? Because this guy is going to complete it in 2 cycles, which will be simply 2 cycle times, 2 times the cycle time, that is going to be smaller than what it will require for the 400 megahertz clock. So again, it would depend on what kind of instructions that we are looking at. Are the instructions dependent on a set amount of time, or are they dependent on the number of cycles that go into it? Now, so short answer is no, because there is IO time that is involved. What are some other times that are also part of this execution time? There might be some time spent by the instruction for doing the operating systems related tasks. We are not accounting for that, right? So outside just the CPU time, there might be other times that you cannot just put into this question and say, yes. You will have to say in general, no. So let's now ask a less ambiguous question, which is, will the CPU time, we are just simply focusing on this, will the CPU time reduce to 4/5 of the original value? We have a 500 meg clock, we have a 400 meg processor. If I just look at the CPU time, will it reduce to 4/5 of the original value? Well, again, there are other things which are going to spoil this. Oh no, it may or may not, right? So in here, the add instruction, I just took an example where the dependence is on total time. Over here, the dependence is on cycles, right? So if there are instructions that depend on time, not necessarily the add instruction, maybe some other instruction, then the improvement in performance, improvement in processor speed doesn't help. Only if the instructions are directly dependent on the number of cycles, only then changing a processor benefits us. And also, think about it in other terms. Let's expand on this. Suppose you have an adder, right? So suppose you have a circuit that is adder, and you give it 2 numbers, A and B. It is supposed to give you answer A plus B, right? Now, is it happening all the time, or inside a computer this happens at specific times? Who controls when the operations happen? The user, FSM, okay, so finite state machine, but it is clocked, right? We need the clock inside our computer to be that manager of when the tasks are happening and when are the results being stored, when are the instructions being fetched. All those things are happening because of that clock. That is the reason why we need the clock, to manage our time. So when the clock has maybe a low to high edge or high to low edge, rising edge or falling edge, then maybe we are taking the 2 numbers, adding them and responding to that, giving out the result. Can I do this addition operation infinitely faster, or will I have certain amount of will I need to wait because I have a circuit that is being clocked at a certain rate? There will be a wait period. Yeah, right. So I'm going to have this particular circuit, because it is a hardware based circuit that is going to take 2 numbers and add them and then give out the result. I cannot simply enter the numbers all the time. I would need to wait as long as there is the propagation delay of the adder, right? So even with the 500 meg clock, or even faster 1 gigahertz processor, 3 gigahertz processor, there will come a time where you will have a bottleneck. Okay, I cannot go faster than this because my circuit itself will not support it. All right, let's come back to this. So we were trying to answer this less ambiguous question about, okay, what if I just focus on CPU time? the amount of time an instruction spends inside the CPU. Can I maybe compare that? Can I comment on that? Now, the problem with that is when you look at the CPU, it is getting instructions and data from the memory. The CPU is performing the operations required, completing the tasks, and then most likely saving the results back into the memory. Right? So when you talk about CPU time, only the time that the instruction spends inside the CPU, that is consistent. However, the time an instruction takes to come from the memory to the CPU and the results to go back into the memory, we don't talk about that. We didn't talk about that, right? So if the memory system bandwidth, which is the bytes per second coming to the CPU and going back to memory, is not fast enough to keep the CPU busy all the time, then it will not run faster, right? Because we are talking about CPU running faster or not. Well, if the memory is slowing you down, then you will not be able to run it any faster than it can. So again, the answer would be, oh yeah, I'm not sure, then I'll have to look into memory system bandwidth. So bottom line being, yeah, you made the hardware fast, but you also have to use the thing that you made fast. Only then you actually realize its faster nature. If you don't use the fast components, then they're going to be slow anyway, right? Let's try to answer a lesser ambiguous question, which is, if the memory system does keep up with this faster CPU, then will the CPU time reduce to 4/5 of the original value? Well, maybe yes. So this kind of looking into other aspects of a computer keep going on. Which brings me to Armstrong law, which is improvement is proportional to the percentage of the time the improved part is used, right? So it's not just about improving the speed, you actually have to use the components that were responsible for that improvement. Only if you use the improved part, then you can see the improvement overall. Now, performance measurement also depends on other factors, for example, usage. Now, you have web servers on one side and you have supercomputers on the other side, or servers on the other side. What are web servers trying to optimize? If you look at the metrics that we looked at before, say throughput and response time, which one is a web server trying to optimize? A web server is going to optimize response time. However, a server or a supercomputer, say, is going to try to optimize throughput. Number of tasks in a given amount of time. Because this guy, the users are interacting with the web servers to get response as soon as possible. However, with supercomputers and servers, we say, all right, here is the bunch of tasks, take them and just give me the results. So the number of tasks completed in a given amount of time. If there are more, I'm going to be happy. So I'm essentially looking at the throughput over there. Now let's move further and try to quantify the improvement in performance a little bit more. Let's get into the details here. We are going to start looking at a table. In this table, we have instructions in the leftmost column, I1, I2, so on up to IN. These are different instructions. So I1 could be add, I2 could be load, I3 could be multiply, and so on, right? Let me just write them. This could be add, this could be load, this could be store, this could be multiply. All of these instructions, I1, I2, and I'm using capital I as to indicate a particular instruction. Then In the next column, I have the number of cycles being used for that particular instruction. So small c1, small c2, and so on up to small cn. For example, an add instruction requires 3 cycles. This is just for the sake of discussion here. So what instruction taking how many number of clock cycles? 3, for example. Next, number of instruction bytes. These are I1 bytes for that particular add instruction, I2 bytes for the load instruction, IN bytes for the multiplication instruction. In general, I have small I to indicate the number of bytes for the capital Ith instruction. Next, an instruction will have 2 things, right? It will have the instruction, but it will also have the operand. So I'd also need data bytes, bytes required for data operands. So I have small d1, small d2, and so on to indicate bytes per data operands for that particular instruction. In the last column, I have frequency of usage, right? So the I1 instruction is being used F1 amount of time. This is F2 amount of time. This is Fn amount of time. Now, based on Amsdahl law, you're trying to increase the frequency of the instruction that has the smallest CPU time, right? Smallest time that it takes. You're trying to increase the frequency of that. If you do, then you would have reduced the overall time that is taken for all the instructions. So K is representing the subscript here, which is for n different instructions. Let's see. Does the computer count the frequency, or does the instruction come with that information? So here, this frequency is monitored based on an averaging basis, right? So for example, to run a particular program or a set of programs throughout the day, what is the user asking the computer to do, right? So for example, if the computer is being asked to add all the time, then that particular instruction's frequency will go up, right? So it's a statistical number here, right? Because we are asking the computer to do these instructions, right? And the more we add the more we ask the processor to work on something, its frequency of usage would go up. Now, these parameters are best understood by keeping track of their units. So let me go through one by one and take a look at each parameter and its units. C sub k, number of clock cycles for instruction ik. So what is you guys can help me with this. What is the unit for C sub k? Hertz. So clock cycles per instruction, right? So this would be cycles, say 3 cycles per instruction, right? Cycles per instruction. Next, I sub k, this is small I, indicating the number of bytes for that instruction. So I sub k would be the bytes per instruction. And then we have data. Again, D sub k is for bytes. So we have bytes per data operands. Now, why are we splitting up instruction and data, right? Because suppose you're trying to do addition of 2 numbers. Then you would have to have some bytes for the instruction, which is add, and you would also have to have some bytes for the data, the numbers that you're trying to add. So both combined will be, you need to look at both of them in order to complete the instruction. Now at the end you have f sub k, which is fraction of all the instructions used, which are for I sub k, the kth instruction. For example, 20% of the time I'm adding, 30% of the time I'm loading, 10% of the time I'm multiplying, right? So that would be 0.2, 0.3, 0.1. So those would give us our fractions. And of course, when you add all the fractions, you should be able to get 1. So that's your fraction of all instructions used, which are AK. Now with this, let us try to calculate CPI. CPI is a very important parameter that we are going to look at in order to talk about the performance of a computer. Clock cycles per instruction, CPI. And this is an average metric, right? So CPI is the average number of cycles per instruction. So if your instruction set has all these instructions, I1 through IK, that are requiring all these cycles, C1 through Cn, then the average would be simply the weighted average of all the clock cycles per instruction. So I'm using C1 for 20% of the time, I'm using C2 for 30% of the time, and so on. So essentially the weighted average of all the clock cycles per instruction inside the set is going to give me the overall CPI. Right? I'm only using this guy and this guy to find out CPI. Weighted average. Now let's do an example using this concept of clock cycles per instruction. We have two computers in this example. Computer A, the cycle time is 250 picoseconds. So that right away gives us the clock rate, right? Like clock rate should be 1 over cycle time. So that directly gives us in hertz what is going to be our clock rate. The average clock cycles per instruction for computer A is 2. Next, computer B, cycle time is 500 picoseconds and CPI is 1.2. Now, if you simply look at clock cycle time, computer A takes much less time to complete one cycle than computer B. So if I just look at that, I may say that computer A is faster, right? But I may accidentally say that computer A is twice as fast as computer B, right? That would be a mistake, but I may say that if I just looked at cycle time for computer A and computer B. But I also have clock cycles per instruction that I need to incorporate because it would depend on the number of instructions as well for each particular program. Now, other things that are involved in this example: same instruction set architecture, same ISA. ISA is instruction set architecture. Where does this belong? This belongs at the interface between the hardware and the lowest level software. That's your instruction set architecture. Let me just show you where it resides. Right. So here is your application that is running on an operating system, and below the red line you have all the hardware, right? Data path, control, digital design, circuit design, layout, all of that is hardware. And the lowest level in your software, where does it interface with the hardware? That's right there. That's where your instruction set architecture is, right? It's an abstraction that includes all the machine level language for the hardware to work on. go back. All right. So the same ISA, which one is faster and by how much, right? Remember, when we looked at just the cycle time, we were very tempted to say computer A is twice as fast as computer B, right? So we need to figure out who is faster. We need to include CPI and also talk about by how much is that particular computer A or B is faster. Now, why would we ever be interested in looking at clock cycles per instruction? Well, think about this. Computer A is requiring 2 clock cycles per instruction, and computer B is requiring 1.2 clock cycles per instruction. Now, think about this a little bit with an example. Let us take an add operation versus a division operation, right? So if you only had addition operations, you probably require, on an average, fewer clock cycles per instruction. Why? Because the instruction itself is simple. But if you had, say, a division operation, often used, then your clock cycles per instruction are bound to increase because division requires more clock cycles. It's a complicated instruction compared to addition. So if there is a difference in clock cycles per instruction, I also need to use that in my calculation, right? So I cannot just base it off of cycle time. What are we trying to compare? Who is faster? If I want to talk about who is faster, I need to compute CPU time, also called as CPU execution time. What do I have with this guy? With 250 picoseconds, what do I have? Cycle time. What is cycle time? That is okay. So I have this guy as cycle time. And using that, I can also find clock rate if you wanted. Clock rate 1 over cycle time. We can avoid calculating clock rate for this example. So CPU time or CPU execution time is the time taken for CPU to finish one program or task. A program or a task may be several instructions, right? So I'm going to need a variable, say, for the number of instructions. So I'm going to say a number of instructions, and it's the same instruction set architecture for both computers, and I'm going to only look at one particular number of instructions, and I'm going to call that I, right? So I number of instructions for both computers. Next, what is this guy? Let's see, red, all right. Can I say that CPU time equals the clock cycles per program multiplied by the cycle time? Can I say that? These many clock cycles in a particular program, and this is the amount of time it takes for each clock cycle. So if I multiply the two, then I'm going to get the time taken for the CPU to finish one program. What are the units, by the way, for cycle time? uh, yeah, seconds, but I want to break it down into, so time, so it's seconds per cycles, right? You guys see that? Alternatively, you can also write CPU time and CPU execution time as clock cycles per program divided by, if I'm multiplying by clock time there, I can divide by clock rate over there. I can also find, right, but seconds, picoseconds, those are all the numerator there, right? But cycle time, that's time taken for a given number of cycles. That would be seconds per cycles. All right. So let's try to compute the CPU time for computer A. I've got 250 picoseconds as seconds per cycle, and I have got 2 cycles per instruction. So if I take CPI and multiply by I, what do I get? So clock cycles per instruction, that is cycles per instruction. And if I multiply that by I, which is the number of instructions, I simply get number of cycles, total cycles, absolutely. And if I have each cycle, I need 250 picoseconds. So what would be the total CPU time to execute I instructions? It would be the multiplication of the 3, right? Can you see that? So clock cycles per instruction, which is cycles per instruction, multiplied by I gives us the number of cycles required to do I instructions. If I multiply that with 250 picoseconds, which is the time taken for each cycle, I will get the total CPU time. So that would be 500 picoseconds multiplied by I here. Now I can do the same thing for CPU B. CPU time B, 500 times 1.2 times I, right? So that would be 600 picoseconds multiplied by I. Now what do I do with these numbers? I have gotten CPU time here and CPU time here. How do I use CPU time to comment about performance? So let's come back to this question just after a discussion on how is performance related to CPU time, execution time. A better performing CPU should have a smaller execution time. Right? And if you were trying to compare the performance of two computers, say A and B, then performance of computer A divided by performance of computer B is execution time B divided by execution time A. Inverse. And if this comes out to be some factor n, what can we say then? then we can say performance of computer A is n times faster than of computer B, which also means we can say execution time of computer B is n times longer than of computer A. You guys see that? So performance inversely related to execution time. Now let's come back to our previous question. I've got CPU time A, I've got CPU time B. So which one is faster and by how much? If I divide CPU time B by CPU time A, I'm going to get the factor 1.2, which means I can say who is faster? Well, computer A is taking less CPU time, so computer A should be faster. Okay, so that's good. By how much? By how many times? When you divided 600 picoseconds I divided by 500 picoseconds I, you got 1.2. Right, 20%. So go summary here. Don't just look at cycle time, don't just look at CPI, look at both the cycle time and the cycles per instruction in order to compute the CPU time for each computer, then compare. All right, let's move on here and talk about other important averages. One is the instructions per cycle, IPC. Now, why do we need to talk about instructions per cycle? It's just the reciprocal of cycles per instruction, right? 1 over CPI gives us instructions per cycle. But why do we need to talk about that? Why just not be okay with CPI? To answer this question, let me ask you this. If you look at CPI, right, cycles per instruction, what do you think its value should be? Ideally, if you had to associate one value with clock cycles per instruction, what would you want, right? So you would expect that the clock cycles per instruction is more often than not 1, meaning one instruction gets completed in one clock cycle. But often you will see that on an average, CPI can also go lower than 1. So it's doing more than one instruction in one clock cycle on average, which is why you look at IPC, the average number of instructions per clock cycle. What are the units over there? Well, it's I per cycles, right? Instructions per cycles. So the units are already over here, so that's fine. All right. The average length of an instruction in bytes, how can you compute that? If I go back to the table here, we are looking at average bytes per instruction, right? I1, F1, I2, F2, and so on. So the weighted average of the bytes that we need for each instruction gives us the average length of an instruction in terms of bytes. The unit would be in bytes. Next, instruction is one thing, we also need data operands. So the average number of data bytes per instruction would now, instead of I1, I2, and I3, we need D1, D2, and D3. We still need to do the weighted average based on the fraction of time the CPU spends in working on that particular instruction. Now, this is for instruction, this is for data. However, if you wanted to complete one instruction, right, memory accesses per instruction. When you do a memory access, you do the memory access not just for the instruction, but also for the data. And if you're doing that, then for each instruction, you would look at I1 plus D1, weighted, I2 plus D2, weighted, and so on. So this is just for instruction, this is just for data for that instruction, and this is for the memory accesses per instruction. Now let's take a look at instructions per second. How do we find out instructions per second, and how do we relate that to some of the other parameters that we have looked so far? MIPS is a short form to indicate million instructions per second, right? I don't want to talk about 1,0,0,0,0,0 instructions per second. I just want to shorten it up and say these many, say 300 million instructions per second, right? But one thing that I want you guys to be careful about is that there are two MIPS that you will see at the beginning of this course. One MIPS is for million instructions per second, and the other MIPS is for microprocessor without interlocked pipeline stages. So it's the instruction set architecture that we are going to look at in detail in the next couple of weeks, or going forward. So be aware of that difference, and depending on the context of the problem, you will have to use one or the other, right? So right now we are looking at million instructions per second. All right, let's come here. So what is MIPS? MIPS is take the instructions per second and then divide it by 10 to the 6. That will be the value in MIPS. Very straightforward. What is instructions per second? Well, for instructions per second can be computed by using instructions per cycle. What is instructions per cycle? We called it IPC, right? Which was 1 over CPI, clock cycles per instructions. And you multiply that by cycles per second. So 1 over CPI multiplied by cycles per second, that's what gives you instructions per second. And then you divide that by 10 to the 6 to get million instructions per second. Pretty straightforward. Now this is the summary of our performance equation. This is essentially your classic CPU performance equation that we have written out here to calculate CPU time, right? One equation that can be used to interrelate several of the parameters that we would look at when quantifying performance of a computer. The first one is instructions per program. How many instructions are required to complete one particular program or one particular task? Are they 5? Are they 10 instructions? Are there 20 instructions? That would be going over here, instructions per program, also called as instruction count. Next, you multiply that with clock cycles per instruction. What is clock cycles per instruction? That is simply your CPI. And at the end, we have seconds per clock cycle. What is that? That is simply your cycle time. So take the number of instructions per program, multiply by CPI, multiply by the cycle time, and you get your CPU time. We have used this before, right? We used this in the context of comparing computer A and computer B. We had I over here, We had 2 and 1.2 over there, and then we had, I believe, 250 picoseconds and 500 picoseconds in the other, right? So in general, you can just use this, and you get to CPU time. You divide one CPU time with the other to comment about performance. It's just going to give you the reciprocal ratio. Now, the performance depends on different aspects of a computer. So for example, if you wanted to improve the algorithm of your program, then that affects the instruction count and may also affect the clock cycles per instruction or cycles per instruction. How do you think algorithm affects instruction count? Well, if somebody is writing up a very elegant algorithm that can be executed with smaller number of resources, then that is supposed to be superior algorithm, right? So if you are able to do it in fewer number of instructions, the same task, then you are essentially changing the algorithm, and that affects instruction count. Also is right there, right? Number of instructions per program. So by changing the algorithm, you do it in a faster way, better way, fewer number of instructions. Because there will always be a bad way to do it, right? The bad way of doing it is more number of instructions to do the same thing, right? Instead of writing 10 lines, you are writing 15 lines of code, for example. That is doing more work than necessary. Next, it could also affect the cycles per instruction. We talked about the example of addition and division earlier, right? So if a particular algorithm, say, requires more and more divisions, then you are increasing the clock cycles per instruction, right? Because that algorithm relies on more divisions than other lower CPI instructions. Next, programming language. It also affects instruction count and it affects clock cycles per instruction. How? Well, for example, if you are looking at, say, Java, right? Java has, a heavy support for data abstraction, which means that it will require many indirect calls. What will that do to CPI? That is going to increase your clock cycles per instruction. And because it's a programming language and you will be writing some source code that will be translated into machine language later on, it also affects your instruction count. Next, you have the compiler. Again, affects both the instruction count as well as the clock cycles per instruction. What is the compiler responsible for? It is responsible for translating the source code into machine language code, right? So if it is doing that in an efficient manner with fewer number of instructions per program, that's how it affects your instruction count. Then now the last one is the instruction set architecture. It actually affects all aspects of CPU time. Affects IC, affects CPI, affects clock time, cycle time, all three of them. Because that is what is at the interface of your low-level software with the hardware. We'll take a look at all these when we actually look at instructions and we are executing instructions. We are finding out the number of instructions. All of these will start making more sense, how it affects them. All right, so CPI depends on what kind of program is running on the CPU. And knowing what kind of program runs on the CPU, you can help design a better CPU. For example, if you know that you will be spending a lot of time executing multiplication instruction, then we could invest in faster multiplier circuits, right? So the thing that gets the highest fraction of usage, invest more money in that. We talked about how clock cycles per instruction, how they do depend on the kind of program, right? So for example, if the easiest way of I think about it is I take a complex operation, say like a division operation, is if I'm going to be doing division operation as opposed to say something simple like addition, then I will push my clock cycles per instructions up. It will go up because of that. Now let's try to put all of this in perspective and focus on where that instruction architecture lies. At the top of that red line, you have your application that is running on the host operating system. The operating system itself has firmware and your compiler. So those are your lowest level elements of your operating system. That's what interfaces with your hardware. And to translate that to the machine language that everything else below that understands, you have your instruction set architecture. So the topmost elements of your hardware are what? Instruction set processor and the I/O system. Underneath that, we have all the things that we learned in the previous class: data path, ALU, registers, the control unit, all of that go over here, which are made up of digital design that can be further looked at a lower level in terms of circuit design and layout. So if you want to sort of improve overall performance, then you need to start looking at things that are at each level, right? Innovate at each level, because it's going to change how your next level operates. For example, when we looked at, when we are trying to compare the speeds, we said it's not just important to increase the speed of the CPU, we also need to look at the memory, right? So if the memory is not able to keep up with the pace of the CPU, then the improvement in the speed, it doesn't help us. So the computer architecture business involves the technology that's used, the applications that are run on the operating systems, the network. Networks are very interesting, right? Because when you think about computer network, it is not like something typical like our input-output devices. The input-output devices that we are very used to, such as a keyboard or a mouse or a camera or a microphone or a display, graphic display. These are all very traditional, either I or O, either input or output. But network has a different set of challenges because it's both input and output. All right, now you guys can get into activity 3. Just for when you are computing the numbers, please round off your clock cycles per instructions to 2 decimal. And we will continue our discussion on role of performance on the next class. I will be here monitoring the meeting here as well as the WebEx team space. So feel free to engage with me wherever you want. The activity is pretty straightforward, just the application of the formulas that we looked at. It will mainly be right here. Right? As long as you're keeping track of the units, you will be in good shape.